Moving on with homework 2, let's go to problem 3. The statement for problem 3 reads as following. Calculate the planar atomic density in atoms per square millimeter for the following crystal planes in BCC chromium, which has a lattice constant of A is equal to 0.289 nanometers. In this problem, we will only be solving part B, which is plane 110. To begin, it'll be best to first start off by drawing our plane and our unit cell. And to do so, we take our plane values and we reciprocate them. So we get 1 over 1, 1 over 1, and 1 over 0. Working that out, we get 1, 1, infinity. This pretty much lets us know that our plane intersects at x is equal to 1, y is equal to 1, and revolves around the z-axis. So we get x is equal to 1, y is equal to 1, and revolves around the z-axis, which will look something like this. We can draw it over here on this one as well if it's easier to see. After we got our plane drawn, let's recall what the formula for the planar atomic density is. So the formula for planar atomic density is the number of atoms in which their center lies on the plane over the area of the plane. All right. In order to help us determine the number of the atoms in which their centers lie on the plane, let's draw a 2D representation of the plane that was found. So we have 4 1/4 atoms which lie on the corners of the plane, and we have the body-centered atom which lies in the center. Now right off the bat we can see that one center of one atom lies on this plane, which is the body-centered atom. But if we were going to put the 4 quarters together, we get another atom. Therefore, another center lies on this plane. Therefore, we have 2 atoms in which their center lies on this plane. Therefore, giving us a total of 2 atoms. Now let's determine the area of the plane. And for this, let's scroll back up to the unit cell. If we take a look, this length is the lattice constant, which is represented by A. Therefore, on the 2D representation, that side is equal to A. If we take a look at the other length, we cross a face. And if we recall, a face has sides A and A. When we cross, which is this length, that length is found to be rad 2A. Just plug into the Pythagorean theorem, a squared plus a squared is equal to the desired length you wish to find squared, and you should get rad 2A. So going back down here, this length is rad 2A. When we multiply those two together, we get rad 2A squared. Since the lattice constant was given to us, we can plug in and solve for the planar density. So we get 2 over rad 2 multiplied by 289 times 10 to the negative 9, and that value is squared. This will then give us 1.699 times 10 to the 19 atoms per meter squared. However, we're not done at this instant. If we go back up to the problem statement, we need to recall that it wants the solution in atoms per square millimeter. So we need to convert. So we take our value in atoms per meter squared, so 1.699 times 10 to the 19. And we multiply that by 10 to the negative 6. Now we'll go ahead and convert it to atoms over millimeter squared, which ends up being 1.699 times 10 to the 13 atoms per millimeter squared. And that is our solution to problem 3b. As mentioned, A and C, the two things that really change is one, drawing your plane, and secondly, finding the area of that plane. But if you follow these same steps, you should be able to arrive to the correct solution for A and C.